And yeah, so this is chapter 5, and we will not cover the complete chapter 5 because we will skip some parts because yeah, you can read on your own if you like. So we'll go through chapter 1, 5.1, 5.2, 5.3, and then we will skip 5.4 and 5.5, and we will do 5.6 and 5.7. So those two that we will skip, this is 5.4 logged consensus and 5.5 randomized consensus. But we will sort of have a randomized consensus anyway when we will discuss Bitcoin, hopefully. So this is one type of similar protocol. Yes. So yeah, regarding labs, I had some questions like who if you did some of the labs in previous semesters and you were approved and such. So in the Discord there is a I wrote a post in the announcement channel where I say that which labs from previous semesters has like an equivalent in this semester. So please check that table, and that's it regarding labs. Oh, one more thing. The deadline for lab 3, this is on Monday already. So please, if you didn't start yet on this lab, always there are some students that are kind of late. So please just try to do this and find a group today or tomorrow so that you don't fall behind. Because lab 4, it will be really the main lab that you will like do in this course. The lab 4, this is like the basis for lab 5 and 6 as well. So if you do a good job on lab 4 and you really understand what's going on, then lab 5 and 6 will be very easy for you. So on Monday I will spend some time to discuss lab 4, which is about implementing Paxos or multi-Paxos, and I will try to give sort of a overall overview of what you need to do, and maybe give some hints on possible ways to solve it. Because the description that we have on the labs is quite long, and yeah, I some students maybe have problems to get started on this. So yeah, I will do that on Monday. But yeah, as I said, this lab 4, this is very, very important for you to do good job on. It will also help you with the report if you do a good job on that lab. So that's that. And regarding people losing access to the course, the canvas, and all those things, well, I reported this issue to the exam office, I guess 1 week ago or so. And I don't know if they fixed it for you guys yet or not, but yeah, I didn't hear any more complaints that people don't have access. But yeah, if you still have problems with accessing the course, or it's not signed up to the exam or the evaluation, then yeah, it would be great to know, because they must fix those issues. All right. So the topic today, consensus, and you all know regarding lab 3, part 3, do you have any suggestion how to start it? Okay, you don't have access yet. Okay, we can take this question with lab 3, part 3. Okay, I will just remind myself what is part 3 in the labs, because I don't remember exactly. Yes. So part 3 is this distributed leader detection. This is part 3, right? And yeah, this is like we have part 1 to just implement the failure detector here, put in the variables we need and all the functions, pass the tests. Same thing with task 2, put in the fields. This is you can all do this very easily. And part 3, this is maybe the most challenging part of this task. And so how to start this? Is your question, how to start working on this? Well, first, first you need to get the overall architecture of your system right. So we know that we have I don't know if it's if I go to my previous presentation that I had, maybe regarding this one, and we had some protocols, maybe it was in the broadcast actually. Let's see. Yeah, oh, okay, we can use this one. And I wonder if I had, I just wanted to show you, maybe it was with the heartbeat. We already did everything so fast. Oh, it must be here, right? So heart. Yeah. Here we are. Great. So this is kind of your how the system works, or the distributed part 3 application, that you have not only 2 processes, but you have, for example, 3 or 5 or however many you like, and they are all sending a heartbeat to each other, and more similar to this protocol, that they are sending a heartbeat, and then they are waiting for a heartbeat reply. So in this lab, we have 2 types. Heartbeat request, we call it. This is when one process is sending the heartbeat out, and then he's waiting for a heartbeat reply. this is the basic messages that will be exchanged between the processes, and then what we have is like a all-to-all message exchange, which is maybe can be seen here, for example, that that in the second phase here, everyone is sending the message to everyone, and this is what you will have in the heartbeat, that everyone is sending to everyone, like you are sending the heartbeat request to everyone, and get the message back. Okay, the problem is to set up sources that talk to each other. The problem is to set up sources that talk to each other. So what's the challenging part with that specifically? Is it the network layer? Let's see here if there is some. Yeah, the network layer have some questions about, because I think you can use still some ideas from, for example, this U-echo thing here. Because in the lab 2 you did this U-echo task, and here it's using UDP, and you can choose yourself if you want to use UDP or TCP. But here you have a function serve UDP, which will your solution will start listening to commands, and the send command. This is typically you can almost just copy this function here and use this for lab 3, just to say that okay, now we are sending heartbeats. To show how the elect each other. Well, I guess I can show you some hints there. Just so this will be. Let's see. So I will show you some tips here. Don't tell the TAs that I showed you this, because it will be a secret between us. Okay, but so here's one possible way that you can do these things here. That you have two separate packages. Like you have your detector package, which is what you are asked to implement here. These two, they yeah, you can change the namespace how you like, but these two you leave as they were, and then you create a new package which will be, for example, you can name this network, or you can name this whatever you so choose. But the idea here is that this will contain a main function. So you need to have one file that has this package main, and it must have a function also called main. Yeah, here it's a function called main. And the first thing this thing should do is to have yeah, it should set up the network to define its own ports, etc. And you can choose yourself if you want to read the ports and IPs of the different servers from a configuration file, for example, or you want to hard code those things, or you want to pass them in as like a command line option. And I can't. So, for example, in this particular solution, it's trying to extract the IP and the port. Yeah, no idea what this does, but yeah, the idea is that you will you need to know from beforehand what is the IPs and port of your the machines that you will connect to. So yeah, I think in this particular solution, there's another message added that allows you to add the service runtime. So the question, does it have to be on PITOs with different IPs? No, you can also run this on like Docker containers or on virtual machines or on PITO. Yeah. So, but if you, for example, use PITO, then you need to kind of know which PITO are you using and what IPs are you starting to listen on. So you will have, like, the main thing is that you will have a go and serve UDP or serve TCP. So this is, you're starting you're starting your server to reply back the heartbeats in a separate go routine. So if we didn't put this go here, then this solution would not work. This is very crucial that you start this in your own go routine. And yeah, I guess this one serve UTP. So I will show you this function here. So yeah, you see this function. It boots up, and it does this initializing things. It adds new nodes to the failure and little detector, and then it goes into this forever loop here. And only in this one we are constantly trying to read from the UDP. So this function, it will be kind of stuck on this UDP line here, that it's trying to read from something from the network, and once it reads the thing from the network, it unmarshal it, or and unmarshal is also called deserialize in other languages, and it's deserialized into this message here. So probably you will recognize this message if we can find it wherever it's defined. Yeah, so this is something custom made, I guess, but yeah, let's see what happens. So you deserialize the message, and then it's like sent to a handler here. And if we check the handler, you will see now that it has like a case, a switch case for heartbeats. So whenever you get a heartbeat message, you can simply deliver the well, you like extract the fields from the message itself, like who is it from and who was it to, and yeah, you can also get this request boolean, and you construct a heartbeat from this, and then you pass this to your failure detector in this way. And I guess this, so only thing now I'm thinking that this should write back a heartbeat reply, right? So where is that down here? So you marsh, you unmarsh, you handle this message, and this returns a new message to you. Return. Yeah, unless it's in this function. So this function takes one in and handle incoming. So if this is a request, yeah. So if it's a request, yeah, you send it back. You change the order. Yeah. So that's great. So then you, where are we? Yeah. So you write back the. So if you receive a request, you write back the reply this way. So is it clear? Does it make sense, this thing? Is it possible that all nodes be on localhost? No, that will be too easy for you. I mean, you need to put this on different IPs at least. Because what's the sense of having a network communication if you're all running on localhost? It's kind of cheating. So yeah, unless you run on a virtual machine or Docker containers, then yeah, you need to be on different machines. But you know, if you already made a solution that can work on localhost with different ports, then basically you have everything ready. You just need to change the IPs. It's what's the problem to run it on different machines? Yeah, you can use Pitta machines or Docker containers or virtual machines. You choose yourself, but the main point is that you need to show some network communication here. Yeah, debugging. Yes, I agree. That's the one big challenge in distributed computing, and I can tell that it only gets worse. you're now on the most simple protocol here with the heartbeats, but you know, when you will move on to lab 4 and 5, 6, then you will also face this problem with distributed debugging, let's say, because you have different nodes can have any different state. The different processes can be do something, they can be blocked, and you cannot make progress. And this is like one of the key challenges that is in distributed computing, that makes it so much more difficult to create algorithms compared to those which is only running on one thread or in one machine. Because in this field, in distributed computing, you always have to think about that your algorithms is being executed concurrently and on different machines, and they can have different timings. They can be different load like processor load and those things. That that's really what makes it difficult. So that's very natural that you feel that way. Yeah, of course you will you start the development on localhost, and only when you can finish, or when you're sort of confident that the algorithm works on the local host, then you will try it on the different machines to like confirm your belief. But if we said that for example that we can just implement algorithms on localhost, then it wouldn't really be distributed computing. It would be kind of just computing. That, you know, it doesn't make so much sense to me, at least, that we that if we say that we are distributed computing, then we need to somehow isolate each peer or each participants in the algorithm that is participating. And also, like if we say that we can handle F failures in these consensus algorithms, and if all the consensus algorithms were running on the same machine, then in effect we would only tolerate one failure, because even if all the algorithms are running concurrently, it's still on one piece of hardware. So we really don't want that. But yeah, to debug the things, then it's useful, as was suggested, just try this on localhost, implement some unit tests, for example, and you can, actually you can really solve this on localhost, like get the algorithm to work, and only you need to demonstrate to the TAs that your solution works on multiple machines. But yeah, but I think that really, if you make everything work on localhost, then it's not a big step to make it work on different machines. It's a small step, but yeah, it's definitely more challenging with debugging, to figure out where is each pair stuck. And you know, here in this example we have only 3 or 5 pairs, but imagine that you have 1,000 or 1 million that are participating, and then you cannot, if we had, for example, 1 million participants, we couldn't use this approach that we are just writing to the console, because we cannot go through 1 million console outputs to check where everyone is stuck. So it's really like a fundamental issue in distributed computing to have debugging, and they have many tools for this. For example, they have one called Grafana that you can that people are using that I don't know if this is the website actually, but this one. People are using, for example, this Grafana, then it can like read outputs from many machines to get like logs and things like that. So that's one tool that's very popular. And another one is Splunk. It's kind of different solutions, but the Splunk, it's more like big data angling, I would say. But anyway, it can serve the same purpose to give you some like it can like aggregate a lot of logs from different machines and give you like one place to read. So like, for example, in the case that we had 1 million pairs, then it could sort of collect all those 1 million for you, and so you would only read like from the Splunk or from the Grafana, for example, to find out where the algorithm or the peers are stuck. But yeah, you don't need to use these tools for these labs. I was just saying that this is specialized tools that is very expensive, and people used a lot of time to develop these tools just to solve the issue that you mentioned with debugging and distributed computing. That yeah, it's a big challenge, and it's some well known in the industry, these things. But yeah, okay. I hope it made sense with the introduction to the lab. But yeah, and there will be a lab day tomorrow where you can come to the what's it called, the room here on the campus, and the TA should be here, and you can ask questions, and probably they can even better explain to you, give you some suggestions like in person. Then it can be some difficult to do it in this format. But yeah, all right. So now we already spent a lot of time on that, but it's very important. But yeah, come tomorrow to the campus if you are feel some difficulties with Lab 3, and we will try to help you the best we can, because once you grasp, I guess the whole idea of the lab, it's not so difficult actually. So yeah. Yes. Okay. Consensus. We already discussed consensus a lot last week in Paxos, and Paxos, this is like a implementation of consensus, you can say, for example, or it's a consensus protocol. And yeah, Paxos is maybe the most well-known consensus protocol, but of course there are 1 million other ones. But yeah, I feel that when we discussed Paxos, we went through the protocol and all the steps and such. Then it will be, if you have this as the baseline, then you can more easily understand other ones. Yeah, please, if there's any questions for any of the algorithms that we will go through, then please just pause me, and I can perhaps try to show you equivalent protocol steps in Paxos, because you will see that a lot of these ideas you will find them again in different algorithms, but of course there are slightly differences between them. But yeah, the main two primitives for consensus is the propose primitive, which is the act of proposing a value, like your give a proposal for a value to so that the network can reach consensus on this common value. So the proposal is the act of suggesting or a value that you want to the network to reach consensus of. And then the decide, this is the primitive that the decision has been made on that particular value or another value. But always you have these two main primitives in mind. And yes, consensus, this is has like we have a saying in norsk, kjært barn har mange navn, and this is kind of like this, that you will find this under many names, and these protocols here or problems, like total order broadcast, atomic commit, or terminating reliable broadcast, they are kind of equivalent in such way that if you can solve one of these, then you can translate this solution to the other protocols or problems. Yeah. So just keep that in mind, that when you read these particular protocols here, then they might be the same thing that you already read before, but it just under another name, which is like a common thing in computer science in general, that we like to have many names for the same thing. Yeah. The first protocol here, regular consensus. Remember, we have the code word help, which we talked about before, regular. And now when it's regular, we are only considering correct processes. So regular, it means something that now we are only worried about those processes that are correct. So this is the module description here, and it's similar to the broadcasting properties. Just we have two new ones. We have this integrity, no process decide twice, and agreement, no two correct process decide differently. So these two, C3, C4, they are the properties which is directly related to consensus. And we have the two events, the propose event and the decide, as we saw before. We are now we will look on one protocol here called floating consensus, and what you need to keep in mind is that this process, it tolerates any failures less than n. So the number of failures must be less than the number of processes in the entire system, meaning that you must have at least one correct process. Yes, so I wrote down some notes here, but I thought I had a slide here with the, yeah, all right. Yeah, so this slide was kind of for myself, but now when it's here, this is the main four, let's say, main key points of the algorithm that we will see. The floating consensus, that we have the initial step where all the correct process propose a value, and we have when our round terminates, we move to the next round, and the number 3, it's safe to decide when no new failures occurred in the current round, and yeah, the processes use a deterministic function to select a value. So I will show you all these 4 things. Where are they precisely located in the algorithm? So the first one, yeah. So by the way, you find these algorithms in your books, as you know, or the PDF that you downloaded. But yeah, it can be useful when you're understanding algorithms, just to write notes next to the thing. But yes, so so in this protocol, the first key point was that all the correct process propose a value. So where can we find something like that? Well, it's kind of obvious that we have this C, the consensus instance, and the event takes in a value, and we are adding the value to the 1 here. And what is 1? Well, this is the round. So for the round 1, we are proposing this value, and then we are broadcasting this proposal to everyone else. So the next key point was that we are moving to the next round when 1 terminates. So we are starting on round 1, and we want to see when does this change? When do we move to the next round? So if we look through the algorithm, we can see that there is only one place that this variable is updated. And if we backtrack to what conditions does this happen under, we will see that when we receive a proposal from all the correct processes. So the correct set here, this initially it starts off to be the set of all processes. Whenever we detect a crash, we remove that crash process from the set, and we want that all the correct processes gave a proposal. So that's this thing that we say that the correct process is a subset or equal to the received from round. So that all the correct processes must have answered. And you need to really think about what does this mean, because what is not obvious is that this sign here, that this I guess it's called like subset or equal sign. It means that in this received from set here, we can have received a proposal from a process and afterwards it can have crashed. So that's why this is not an equal sign, because we allow that we receive a proposal from one process, afterwards it crash, and we can continue anyway because we have the leader detector or failure detector abstraction here. And then we have the the, um, the complement here that the decision is the nil value. So we didn't make any decisions, and this is this property tree integrity. No process decide twice. So what it could have also said is that we only decide once, or a correct process only decide once, for example. But they want to capture that it's also possible to not decide anything. But the idea here is that once we make a decision, we will stick to that decision. And this is what you will see in consensus protocols in all of them, that once a decision is made, it will stick to that decision. And yeah, that's what we see here when we get the correct, all the correct processes. They propose something, we increase the round, and we basically send the proposal that we had from before. So we send out the proposal again, and once everyone replies back with the same, like all the there's no failure in the round of the algorithm. Like for all the processes that send out a proposal, we receive the exact same number of proposals in return. So these two are equal for the two rounds, and only then we have the deterministic function, the minimum function, that chooses the minimum value and yeah, make the decision. So that's the four main point of this algorithm, and there's a sequence flow or execution flow here, in which you can see that all the processes, they propose a different value, w, x, y, z, and we have whenever you read such sequence flow, you need to really pay great detail to what messages are being exchanged here, because we see at the end we have a decide for w, and well, why does this happen? Because the process P, it sent only one proposal before crashing, and this proposal was only received by the process Q. And this is why that we can see on the process R and process S that they know only about these values, X, Y, Z, X, Y, Z, because they only received these proposals from each other. And only the process Q knows about W. But since that this condition with no crashes is detected for the process Q, it's already deciding on this value in round 1. So it's calling the decide on the value W. It's kind of under this dot line for some reason. I don't know why they didn't move it, but it's deciding on the value W, and the argument or the reasoning behind that is that is the minimum of these values. And only in the round 2, the 2 other processes can decide, because they didn't detect any new crashes between round 1 and round 2. So what we can see, like we if we want to consider performance of this algorithm here, then we need to look at message exchanges, and we can see that in the best case, if we don't have any failures, this can decide in only one round or one communication step. Imagine if this process P didn't fail, then we would reach a decide on already the first round. But in the worst case, we have one. We can have one additional round for each crash that happens. So if one of these 3 crashed, then we will move to round 3, and again, one of those 2 crash, we will move to round 4, and yeah, that's the last round. And in each round, we have also n squared messages. So how do you know that? Well, it's easy, because we have n processes, and each of the n process is sending a message to n processes. So it will be n multiplied with n total messages that you can see here. So in the worst case, you have n squared messages in n rounds, meaning that in the worst case you have n cube messages, because you have n multiplied with n multiplied with n cube. All right. Moving on to the next, hierarchical consensus. It's still a regular hierarchical consensus. Yeah, this is the algorithm, but kind of I might want to show you this one first, maybe. We are so great, we can continue to start with the algorithm itself first. The idea here with the hierarchical approach is that we have a rank function, so that each process is given a rank, and this is also quite typical in consensus protocols. We have the ranking here, and I think that this ranking, it works in such a way that the lowest rank takes precedence. So meaning that if a lower rank propose a value, then or or a higher rank proposal value, then all the other ranks must follow that suggestion. And we can see that also here. So we propose a value, and we will broadcast this once, and when we receive the deliver message, we will filter out those lower ranks, and we will choose the higher ranks to take precedence. So the sequence flow is here, and the one more important step that I failed to mention is that we can only decide or each process decide only once in each round. So only one process decides in each round. So we start off with the for process, and the first process is sending the value W, and this time it reaches all the three processes but at different timings. And since the process P is kind of the leader in round one, it would decide in round one, but it crashed before being able to decide. And since process Q is the leader of round two, it ignores the value from the P, because in that round it is like the leader, or the one with the highest rank. And the process Q is sending the value X out, and since it decided this value and it's not crashed, then the other process all decide X in their round. So well, what is the most best performing algorithm between these two? What was it, flooding consensus that we saw first, and this one. The main difference is that in this algorithm here, we don't have the all-to-all message pattern, so we have less messages. We have only n messages in each round, not n squared. But the disadvantage is that we have always n rounds, so that we have more communication steps, because we always need to have so many rounds that are processes. Yes, and the next one I wanted to discuss is uniform consensus, but at least I need a break, and I was thinking that we can continue at 10:40, and we will do that. put up a timer because that's very good. So let's continue 10:40 a.m. in 14 minutes. All right. All right. Everyone is ready for the next part, I hope. So let's continue with uniform consensus. Let's move this on. All right. Great. So, what is uniform consensus? This is very similar to the thing we saw before with the uniform broadcast and regular reliable broadcast. That now we are also considering that we don't allow any process to decide differently, even if they are faulty. So even crashed processes cannot have decided a value on its own without the rest of the network also deciding that value. And we saw before with the Paxos that this could potentially lead to inconsistencies. For example, if a process already wrote to a database or replied to a client, and the other processes didn't learn about this decided value, then you could get the inconsistency. So uniform consensus, it deals with that, and the algorithm that we will see, we will see a flooding type, and I guess a hierarchical algorithm, and they are working similarly, and they also rely on this perfect failure detector, the fail-stop model. So the algorithm is presented here, and if you have a keen eye, you will see that most things are very, very similar, but the main difference here is that we can no longer decide after one round. We need to always let the algorithm run n rounds before we make a decision. So yeah, remember that for the regular consensus, we could make a decision after two consecutive rounds where there were no failures. But for the uniform consensus, we need to let all the rounds complete, and only then we can make the decision deciding value. So now we no longer have the worst case and the best case performance. It's always the same performance here, that we always have now n communication steps, n rounds, and in total this will be n cube message exchanged. So that was that. And well, just to jump directly to the next algorithm, the hierarchical approach. Remember, it has the ranking, and each process just maintains a single proposed value, and whenever it's round, the rank is equal to its own the round is equal to its own rank, then we are broadcasting our proposal. And if we receive a proposal from a more important process, then we adopt that value, and we make this decision based on that. So more interestingly, perhaps is the or one more thing here is that you can see with what modules is this algorithm building on top of, and we can see, yes, they are both using the perfect fail detector, and they are both using the best effort broadcast, but the hierarchical, it's also using the perfect point-to-point links, and this is due to the acknowledgement message that is being sent. And also this algorithm, it's adds communication steps for each failure, or two more communication steps for each failure that occurs. But yeah, this one is now we are in the fail noisy model, which is similar to the same actually as the one we saw in Paxos. And this algorithm it's kind of more let's say realistic, or and also more involved. So we will spend some time on this, and yeah, then we will see the Byzantine variants. But yes, the important thing to note here is that these now we will look on fail noisy, and this means that in the fail noisy model we cannot have the perfect fail detector, only the eventual fail detector. So remember that difference, because we no longer have the fully synchronous network. So the way that this is presented in the book, it's with what they called epochs, and you can already think about this as the rounds that we saw in Paxos, that we try to reach consensus in each epoch, and if we are unable to, then we progress to the next epoch. And we continue to do this until we reach one particular epoch where we are able to reach consensus. So the way that they present this in the book here, it's with two protocols, one which they call epoch change, and the other one it's called just epoch consensus. So we have epoch change and epoch consensus, and you can already draw some parallels to Paxos, because in Paxos we have also kind of two phases. We have the phase one, which is about the propose and promise messages, and this is related to leader detection or election, choosing who is the leader for that particular round. And it's the same thing here, that this phase one here, or the first module here, it's regarding leader changes. And then the second phase, epoch consensus, it's about reaching the consensus, or if the process should decide on that value or not. Yes, so there is some properties here, and one thing to think about is this time step TS, and remember that it doesn't make so much sense to think about this as in the traditional sense, with how many seconds or how many hours on the clock. So whenever we encounter timestamp, we can think about this as a vector clock type thing, so that it's just a number that can keep increasing. And that this is also captured in the first property here, monotonicity, that this timestamp, it's only growing. So whenever you see one epoch with one timestamp, and you later find another, or see another epoch, then the later epoch that you saw, it must have a higher timestamp. Yes, and yeah, we can move on to the algorithm here, and I think you saw this already in Paxos, and so and also in the leader detector algorithm, but this one is using the eventual leader detector here, and we can see that there's one kind of interesting step here with this TS is defined as TS plus N. And this is the type of question that, I would ask you on the exam, but we will not have this one. But anyway, what does this mean? What is it? Why is it like that? What is N, first of all? So N, this is the number of processes that we have. We have always n processes in our entire system, and what this do is very similar to what we saw in Paxos, that we are increasing like our timestamp or our let's say timestamp with n every time, and this partitions the epochs in such a way that every process or the leader, it's changed every or rotated every timestamp, and we will go through all of them until we reach n. And it also allows us to, if we have a high timestamp, we can easily find out who is the leader in that timestamp. So try to see if this makes sense for you, this timestamp. Yes, and yeah, you can see that here the timestamp it's initialized with this ranking function, and this is the idea here is that this must be unique between all the processes. And if we if this TS is unique and well, it's unique and it's less than n, then we can keep increasing or adding n, and they will not have a collision between them. So yes, that's the leader change epoch. So the epoch consensus, it's similar to the uniform consensus, but one thing one key difference here is that we are in the fail noisy model, and due to this we always don't have this strong guarantee that we will reach consensus in a particular epoch. So we must keep in mind that we may reach consensus in the epoch, or we may terminate or abort. These two algorithms, they are combined together, and it for each round it tries to reach, or each epoch it tries to reach consensus, and if it's unable to, it simply continues to the next round. And similar to Paxos, we have the proposed request only to be executed by the leader, and not by all the processes that we saw before. So this is a simplification for us. Well, easier to reason about, I guess. Yeah. So the full module description is given here, and it's might look like a lot here, but these three first ones we already saw in the uniform consensus, very, very similar. It's just now that we have the EP dash in front pretty much. But yeah, for example, validity, we want a value that was actually proposed by a leader in a particular epoch. And we want uniform agreement, meaning that even a faulty process and a correct process must not decide differently. Integrity, every correct process decides at most once. And we have the lock-in property, which we also saw in Paxos, that even if it's kind of related to the integrity property, but it's saying something that about that if some process was able to decide a value in a previous epoch, then it's not allowed for the algorithm to decide a different value in further rounds or the next rounds. Yeah, so we can jump to the one algorithm here. Don't know if the text is too small for you, or, but in this algorithm here, read-write epoch consensus, we have 5 communication steps. And it's the leader that tries to impose its value on the other process. And it has a read phase, and I'm not sure if we, yeah, it didn't show us, but it has a read phase and a write phase, and a decide phase here. And it's first proposing a value, triggering a broadcast to all the processes. They whenever they deliver this, they send this to the point-to-point links abstraction. And whenever we have reached a sufficient amount of these read messages, then we so the leader is proposing this value, and all the other processes are replying back with the read response. And whenever the leader gets so many or more than half read messages, he does the write phase. And in the write phase, it's the similar thing that the process is reply back with the write message, and they update the value that was suggested, or yeah, the value that the leader proposed, plus his timestamp, and the leader, whenever the leader has received more than half accept messages, he broadcasts the decide message to all the processes, and then they all deliver this up the stack. So that's this very nice and easy algorithm to reason about. But yeah, here we have you have 2 rounds for two communication steps for each message type. So we have like the read, it has one send broadcast to all the process, and then all the process is replying back to the leader, and the same with the write, one out and all answer back. Because if you see here, this is not a all-to-all protocol. It's only from the leader to the process, and the process are writing only back to the leader HDL. And if only one phase or communication step with the decided message. So 5 communication steps, and only in each step n messages, and the big O will of course be big O of n for such algorithm. Then we have leader driven consensus, and now we are actually using those epoch change and epoch consensus abstractions that we saw before. So here we have a few things. We can perhaps it will be more easy to show this one first. That we have there are 2 types of requests from the application: the propose command, which is only executed by the leader, and we have also the abort abort request and abort indication. So maybe the most simple or most easy thing to start with is the abort here. That whenever we get the abort message, we continue to the next round here. It's just written in text here, which is I guess fine for our understanding, that we know okay, this is only progressing to the next round with a new leader and a new state here. So the leader proposes, and so it should, on this step, it should say that only the leader executes this propose, and I feel like there's something missing from here. So where's the ETS? Yeah, so okay, the each process runs one epoch, and the timestamps here, they are increasing monotonically, meaning that they are only increasing one way. And whenever one instance is started, you are aborting the previous one. So that's the idea, that when if we want to start a new epoch, we need to abort the previous one and start a new one with a new leader, and it will have such execution flow here. And again, we have the ranking between the processes, and maybe that was what confused me here, because they didn't write this ranking in the pseudocode here, but yeah, it works in such a way that for example, in the epoch 6, then this ranking function turns out that the process Q is the leader for that round epoch. I'm switching these two words, but whenever I say round, I mean epoch. So the epoch here, we have a deterministic function, so that we pass in the epoch, and from that we can know who is the designated leader. And the same thing with epoch 8, it is S, and 11, that's R. So it's kind of, we can kind of already see that it's using the function with a similar approach to here, with the for every epoch we are adding n, or each timestamp we are adding n, which is in this example before, and due to this we know that if we only think about numbers 1 to 4 here, 1 2 3 4, and whenever we get an epoch, we like divide by 4 and take the remainder. So whenever we divide 6 by 4, we get 1, and then we have 2 remainder, and this is why it will be the process 2 here, or Q, that is the leader. For 8, we do divide by 4, and the remainder will be 0, and this is S. And if you take 11 divided by 4, you have 3 remainder, which is the third process R. So this is the ranking function, and this says something about who is the leader in that epoch. So one crucial thing here is that we can not guarantee that all the processes are in the same epoch. And this is also nicely drawn here, that we can see that the epoch 6, it lasts way longer for process R here. So for some reason, the process R, it's very spends a lot of time in the epoch 6 before he realized that he should change to epoch 8. And in epoch 8, we have the proposal of the value 8. No, the value is Z. The value is Z here. And the process P is able to decide on this value in epoch 8. And even, and you can see here that even if process R did not decide on the value Z yet, and he's trying to propose a different value, the value Y, he is not able to do this, because we must respect the property that we saw before, which was named lock-in. Yeah. So this lock-in, I can put it here. Yeah, the lock-in property must be respected in coming rounds, coming epochs. So that's that. Now we have logged consensus. I'll just see if there's something more I should mention about this. No, I don't think so, but is there any questions regarding this uniform consensus here, the leader-driven consensus? Because if there is no questions, we will take a break because I think that we do not need to spend time on the logged consensus here, and also the randomized consensus, even though it's more fun. Perhaps we will go into these things on Bitcoin, I think. So we will jump directly to the Byzantine consensus, and yeah, let's take a short break. Oh, we have a question. At epoch 8, the remainder is 0. So how S become a leader? Well, this is easy because we have only the value 1, 2, 3, 4, but it would be the same if we just chose 1, 2, 3, 0. You know, so if we include a 0 value, then it's still unique for each one. If it makes sense that we can have either we can like switch move things around so that this one will be, or yeah. Well, how they did it in this book anyway is that they have P has 1, Q has 2, R has 3, and S has 0. That means that one of them can be, yes, in every epoch there is only one that can be a leader. So it's a unique value. When you divide by n here and you get the remainder, it will be unique because the remainder can be from 0 until 1 less than the epoch, and you will have exactly so many processes. Yeah. No, I mean the remainder will be up to 1 less than the number of processes. Yeah. Yeah, that's what I mean. So the remainder, when you divide any epoch by 4, the remainder can be 0, 1, 2, or 3. You cannot have a remainder 4 because then you would just have a one more like integer value in your division. Okay. Anyway, let's do at least a 10-minute break, and after this we will so 11:30, and we will go through Byzantine afterwards. All right. Oh, hold. Right, let's close this one. So let's continue with Byzantine consensus. Yeah, we will not go into the most detailed things about this, but we will do some. And remember that when talking about Byzantine processes, they can be arbitrarily faulty, and we cannot have any requirements or assumptions about their behavior. We don't know what um, they will do in effect. But still, we want to have a consensus, and the usual requirement is that you must have um, more 3F+1 processes in the network to tolerate F failures. And yeah, we saw that it's no longer sufficient to have only a majority processes. These algorithms. So yeah, we will start off by looking at two types of consensus protocols. What they in which they they call weak Byzantine consensus and strong Byzantine consensus, or just Byzantine consensus. But the main difference is with this validity property. If all processes are correct and propose the same value v, then no correct process decides a value different from v. Furthermore, all processes are correct and some process decide v, then v was proposed by some process. So this is kind of a long description, but it's only gives us some guarantees if all the processes are correct. But we are more interested in the let's say strong Byzantine consensus with strong validity. If all correct processes propose the same value v, then no correct process decides a value different from v. Otherwise, a correct process may only decide a value that was proposed by some correct process or the special value square. So either all the correct process must propose the same value, or we have the guarantee that that the value will not originate from a Byzantine process. That at least we have the guarantee now that the value, the decided value, was proposed by a correct process, or in the worst case we have this special value square that we use. So now we will see on a concrete algorithm, and it's similar to the ones we saw with the uniform consensus in the noisy model, fail noisy, with the epoch change. And again, we have the same type of algorithm, only now we are in the arbitrary fail model. So the typical thing that you must observe is that we are now using our authenticated perfect links. So this means usually that there is some digital signature or a MAC attached to each message, so that it's not possible to forge this message from from anyone. So only the sender can send a message. The other process cannot forge a message, so that other processes will believe that it originated from a different process. And we don't need to go through the whole logic with epoch changes, but we have special conditions in the Byzantine epoch change algorithm here that we will change who is the leader when we no longer trust the current leader. And since we don't want to kind of act on our own or just become the leader ourselves, we first listen to this epoch, new epoch. We keep this this set here with the new epoch, and whenever we receive a sufficient number of messages that there's a new epoch that we don't, there's a sufficient process that don't trust this current leader more than F. So if it's more than F, it we broadcast this suggestion to change the epoch ourselves also. And whenever any process receives more than 2F of this, then the process changes the epoch and starts or chooses a new leader. So we need first we wait for F processes, and once or F messages, and once we have received F, then we broadcast ourselves, and when we have 2F, we do the switch itself. And it's similar to the rotating leader or round robin type of thing, that where the leader is deterministically decided based on timestamp. For example, using the modulus operator. And complements to the epoch change, there is of course the epoch consensus abstraction, and now there is a change with the agreement protocol here, because now we no longer have guarantees about faulty processes, because remember, they can not follow the protocol at all, so we cannot give some guarantees that they cannot just decide on their own. So the agreement is modified now to only say something about correct processes. And otherwise, it's similar to what we already saw. And there is also one abstractions that we that will be used here. It's called the CC, or conditional collect, and is used to collect messages or collect information in the system in form of messages from all processes in a consistent way. So it's trying to get a sufficient large quorum, and then providing this abstraction to the Byzantine consensus algorithm. So yes, we can go to the algorithm here, and actually I wanted to all right, we can have a look here on the conditional collect, how it's implemented. And it again has a leader that executes some of the events are only executed by the leader, and the important thing here is that when we have the input event here, when we input a message, then the process assigns this message. So it's a digital signature, and then he signs whatever message is requested, and sends this out, and the leader, he kind of aggregates all these messages, verifies all the signatures, and he collects them in two sets here. One is the message set, and one is the sigma set here, which is like a set with all the signatures from all the processes. And whenever we have a sufficient number of messages received, so that we have received more or equal to n minus f. So this means that we have remember, we can tolerate f failures, so that we have received more responses than then failures we can handle. So then we can proceed here. We trigger the send event to all the processes with the messages that we collected, like the set. So this is kind of a abstraction to yeah. The last thing is that whenever a process receive this collection message set, they also verify the signatures here, and then they push this up to the application layer. So this type of abstraction here, it's like a way to avoid the all-to-all message exchange pattern, because now the processes can only send to the leader, and then the leader collects all the signatures and aggregates them together and then sends them out to the processes. Yes, and then this is actually the last algorithm that I was planning to discuss here. So let's keep on going. It's very small. Let's just see here. Yeah, all right. Yeah, it's very small, but I hope you can see. And yeah, in the book they kind of put this to 2 different pages, but I put them together for you here for your viewing pleasure. But anyway, we are using the authenticated point-to-point links and the conditional collect that we just saw. And remember, our goal here is to reach consensus in a Byzantine environment, and we use this epoch approach where we are keep on rotating the epoch or updating the epoch. And as we saw in the previous non-Byzantine algorithm description, we have 2 phases. We have the read phase and then the write phase. So again, we have a read phase and a write phase. So in the read phase, it's very similar, that we send out a read, which is very similar to the Paxos variant, that we send out this read to get the response back from the processes that they will allow us to send a value in this particular timestamp. So whenever we get a reply back, we, instead of doing something directly, okay, we have a question. Is there a difference between the concept of round and epoch? So this is not well. You can say that for this algorithm here that we have discussed with epoch and what we saw before with Paxos, here they use these 2 words for the same thing. That this algorithm, they call this an epoch, whilst in the Paxos that we saw, they call this a round. But this is obviously something that is up to the algorithm itself, that you might encounter algorithms where the algorithm designer decided to use these two words or definitions for different meanings. But for our case, for our purposes, that you can just think about them as the same thing. the epoch and the round. Yes, and yeah, and when we to continue with the algorithm here, I'll be fast so we can end on time, so that you can have your lunch break. But yeah, we receive the read messages from sufficient or from any process, and instead of processing this read reply back, we just send this directly to our conditional collect module here, and this does the this does the work of aggregating them, checking the signatures, checking that they originated from the correct process, and all that stuff there. And only when the conditional collect is in such a state that it has received a sufficient amount of reads and all the signatures match, we continue to the next phase, to the write phase. And yeah, in the write phase, we send the write out to all the other peers with the value that we had was proposed, and when we receive a sufficient number of write backs for the same value, more than n plus f divided by 2, so we have a Byzantine quorum here. Then we send out the accept, and I believe that this is an all-to-all message exchange here, so that not only this is not only done by the leader, but any process that receives sufficient number of write messages, he will broadcast this accept here, and when we receive another Byzantine quorum of accepts, we will decide that value. So there is sample execution, and in my notes here I have noted that this is for epoch 6. Okay, it says epoch 6 there. The process Q with rank 2 is the leader. So we have that we are in epoch 6 as the logic that I explained before, that we have like a rotating round robin fashion type thing, where the leader is decided by the epoch number. Then since Q is the second process, it will be the leader. And yeah, this is confirmed by this figure, because he is the one that is proposing the value, and only the leader should propose a value. So Q, he broadcasts the read message, and this causes the CC, the conditional collect, to collect the states. So what happens next here? Wonder if I have. Yeah. Okay. Yeah. So we do not reach. We have different values you see here that they have different states from before. They have this one has 1, x, 1, nil value, and so does s. And due to this, they so just to remind you, what is this? This is this epoch state here, that you see that these processes has a different epoch state. And well, what is this val? When is this val defined here? We see that this is defined here when we have a sufficient number of write message. So this means that and remember, we have the property BEP2, no correct process decide differently. So due to this, we do not reach a Byzantine quorum. Remember that we have f is 1, n is 4, and 4 plus 1 is 5 divided by 2, and rounded up to an integer is 3. So we need more than yeah, I guess more than 2. Well, if we have 3, it's a sufficient big quorum here. But we don't reach that because they have different values here, and this Q is Byzantine here. So that's why this is aborted, and we progress to epoch 7. In epoch 7, the process Q is still Byzantine. He has this little lightning here. And now in the epoch 7, the process R is the leader. He proposes the value 0 here. Is it yes, the value? No, he proposes the value y here, but we only the Byzantine process actually decides on this value, because the other ones are aborting. But since he is Byzantine, he decides anyway. But the other ones, they abort. But they have the accept message written here, so that we can see that we have a sufficient number of writes, and we then that's why we broadcast the deliver out. Yes. And yeah, I guess that's that. I think we are out of time. So yeah. Well, I don't want to take your lunch break, so if there's any questions about this, we can discuss them on Monday. And I will also do an introduction to Lab 4 on Monday. So, all right, it took some time this, but I hope it was useful. All right, see you all on Monday, and remember the lab tomorrow. Bye-bye.